Okay, so we are doing part B of separations now. We're going to be deriving the Fensky equation for determining the minimum number of stages. Okay, so as of now, what we're going to want to do, I'm going to go ahead and draw out two things that we're going to be using. So that's going to be this XY graph. So YI, XI, we have our usual 45-degree line and our equilibrium curve. Okay, so that's that. And I'm going to be drawing a three-stage process, and we're going to be using this graph essentially when we derive um, this Fensky equation. Okay, so we have stage n and n plus 1. We have stage 0, 1, 2. We have our streams coming down and up. We have our heating powers as well as our condenser. We have our distillate and we have our bottoms. Okay. So just wanted to have that written down. So essentially we're trying to find the minimum number of stages, right? And what we want to do for this is I'm going to go ahead and change the color, but we want to draw in an operating line essentially on this 45-degree line. So on this 45-degree line, we have our operating line. This operating line is essentially a 45-degree line. Okay. Another way essentially we can write this. So now let's say we want to focus on the rectifying part of this, and we know that this equation is essentially R, go ahead and change the color, R over R plus 1. And this is essentially equal to 1, right? Um, we can suppose, right? So this is essentially our operating line. So we can essentially suppose goes up, as R goes up, our R plus or our R over R plus 1 approaches 1. Doesn't equal 1, but approaches 1. We also want to say that this reflux, when is equal to our liquid at stage 0 over our distillate, and we want to essentially not have any distillate anymore. So when this goes up, this is going to go down. So we are essentially saying no distillate, right? And what does that mean here on this graph? As you can see, what does that mean? So essentially, we can go ahead and just cross this out as well as our bottoms. We can go ahead and cross these things out. We don't need them anymore. Okay. Okay. So now what we want to do is we want to go ahead and kind of start deriving this Fensky equation. We're gonna go ahead and start again, of course, like we always do, with a mass balance. So this is gonna be our vapor at stage n plus 1 equals our liquid at stage n plus our distillate. Again, we said that there's no distillate. We can just go ahead and take it out and put it to 0. Okay. So we can also rewrite this as our vapor composition at stage n plus 1 multiplied by our vapor flow at stage n plus 1 equal to our liquid composition. No, sorry, that's vapor. This is liquid. Our liquid composition at stage n multiplied by our liquid flow at stage n. Okay. What we want to do from this point is we can also cross out some things. I'm gonna go ahead and change the color. Make sure I'm still recording. Okay. So we can go ahead and cross out this, and we can go ahead and cross out this. Okay. Now what we want to do now. Oh, I think I'm good. Is we want to apply our partition coefficient, okay? And that is K. So we can say that K, K, Ki is equal to our vapor composition at stage n over our liquid composition at stage n. So essentially what we want to do is we want to solve for this. Solving for this allows us to get, let's go ahead and do that first. So solving for this, we get our vapor composition at stage N is equal to our partition coefficient times our liquid composition at stage N. And we can also do this for essentially at stage N plus 1. So what we want to do is say that rewrite this at stage N plus 1. Okay, and one thing we want to do is we want to substitute this into this right here. Okay, so substituting this, what we get is, let's go ahead and look back up with this. Okay, so substituting this, we get essentially what our light key and heavy key is. So Ki times our Xi at n plus 1 equals our Xi at n. And we can also just do this for J. We're referencing I for our light key and referencing J for our heavy key. So Kj times Xj n plus 1 equals Xj at n. Okay, so essentially this is our light key and this is our heavy key. Okay, so what we want to do now essentially is apply our relative volatility. So we know that this is denoted as this symbol. However, we're looking at this for species I and species J, our light key and heavy key. So I, J, and then this is going to be equal to our partition coefficient of I or over J. And what we want to do now essentially is let's go ahead and rewrite this. So this relative volatility is going to be equal to our liquid composition at N of species I and our liquid composition at stage N of species J. Okay. And we can go ahead and rewrite this for this equation that we just did for our light key and high key and for at stage N plus 1. Okay, so that's essentially what we're trying to look for here. So this is going to be equal to Ki times Xi at N plus 1 over Kj times Xj at stage N plus 1. Okay, so now we can set this up for the condenser, which is again our relative volatility coefficient multiplied. We're going to be now looking at this at stage 0. So this is going to be multiplied by our species liquid composition X at I at stage 0, Xj at 0. And this is also going to be equal essentially because we're going to be looking at stage 2 in a second. Let's go ahead and write that right now. Stage 2, which is essentially Xi1 and Xj1, which is also what's going to go right here, Xj1. Okay. So we can rewrite this as our stage 2, which is Xj2 multiplied by our relative volatility on both sides. Let's go rewrite that again. Okay. So now what we want to do here is we want to combine these terms. So it's going to be a little bit complicated, but we'll go through the process. But combining these terms is going to sum out to Okay, so combining the terms, we're going to get our liquid composition at stage 0 for our light and heavy key. And this is going to be equal to our relative volatility coefficient. Again, we're looking at two relative volatility coefficients. And this is going to be, again, multiplied by the fraction of our light key liquid composition at stage 2 and our heavy key liquid composition at stage 2. Okay, cool. So now let's go ahead and just rewrite this combining term. So gonna look essentially the same thing. We're gonna square this as we have 2. Okay, so it looks good from this point. So what we want to do now is essentially put a more generalized version of the Fensky equation Generalized means we're going to be inputting n, simply n as a stage. And doing that, we get our generalized form. Generalized Fensky. And that's going to be xi at 0, xj at 0, liquid, light, liquid, heavy at stage zeros is going to be equal to, same thing, relative volatility at stage n. Sorry, we're not looking at stage 2 anymore. And then I think this is going to be at stage, I'm not sure if this is going to be, let me go look at my notes real quick. Okay, so we're good. We can go ahead and then multiply this by our liquid light composition at stage n divided by our liquid heavy at stage n. Okay. We now want to go ahead and solve for n. So solving for n, essentially what we get is we get xi at 0, xj at 0 over xi at stage n over xj at stage n. Okay, and this is all going to be equal to, we're just essentially moving this term over. This is going to be equal to our relative volatility at stage n. Okay, so now what we want to do is we want to go ahead and take the log of this. So taking the log of this right here and taking the log of this, we're just going to go ahead and move this out. So n log ij. I don't want to go ahead and rewrite this again. I'm about to go rewrite this in just a second, but we get n equals essentially our log of that term. So that term right here, xi0, xj0 over xin, xjn over n. Nope, we already put that in there, log relative volatility. Okay, so this is essentially our more generalized derived equation for Fensky. And we go ahead and move on to part B. Okay, so we are going to be moving on to part B of the second part of part B for this homework, and this is going to be deriving the Underwood equation for minimum reflux. Okay, so just before we step on to kind of the derivations and our mass balances for this, I just want to talk about a few things. One of them being the pinch point. Now, how is the pinch point kind of determined, right? So we have our x and y's right here. Have our x and y's right here, and let's say we have a operating line that goes along somewhere like this. Let's redo that. The line might be better. So let's say we have a operating line that goes somewhere between here, right? Let's go ahead and draw some stair steps for this. And when we do that, let's start at here. So just not the best representation, but right here, this is going to be referred to as the pinch point, just for reference purposes. And we'll come back to that. And as far as this mass balance, the only thing I wanted to talk about is we're essentially taking a mass balance of these two streams, and we're going to be using the liquid entering this stage to find the equilibrium with the vapor also entering this stream. Okay, so we'll be using this stream. Okay, so starting with the mass balance. Starting with our mass balance, let's keep this clean. So we have our vapor, our vapor flow at stage n plus 1, which is going to be equal to our liquid flow at stage n plus our distillate, right? Just like we've done before, we've done a million mass balances. Now let's go ahead and do a component balance for this based off of what we just wrote. So this is going to be our vapor composition at stage n plus 1 multiplied by our vapor flow at stage n plus 1 equal to our liquid composition at stage n multiplied by our liquid flow at stage n plus the composition of our distillate multiplied by our distillate, or essentially the recovery of our distillate. Okay, so at our pinch point, there are an infinite number of stages, right? So we can go ahead and refer n equal to infinity, right? So let's go ahead and input this in terms of what we have for n. Okay, so we have our vapor composition at stage n, no, vapor composition at infinity multiplied by our vapor flow. Okay, this is going to be equal to our liquid composition affinity multiplied by our liquid flow plus our liquid composition of our distillate, or the recovery of our distillate. Okay. So now what we want to do is we want to apply our partition coefficients. Okay. So applying our partition coefficient K, uh, this will be referred to Ki, which is essentially the partition component of our more volatile component. That's going to be equal to our vapor composition at stage n over our liquid composition at stage n. And essentially, this is what we want to solve for. Okay. So solving for this, we get the, sorry, I messed something up. Okay, let's go ahead and rewrite this in terms of infinity like we did before. So, okay, that's cool. And again, we're still solving for this. Okay, so this at infinity is going to be equal to our vapor at infinity over our partition coefficient of the more volatile component. Okay. So one thing we want to note for though is we want to plug in this term into what we have over here. So we want to plug that into this. Okay. So doing that, what we get is our vapor composition of infinity multiplied by our vapor flow equal to our vapor composition at infinity over our partition coefficient times our liquid flow. Let me go ahead and make my fonts bigger. Okay. Times our liquid flow. Oh, this is much better. Plus our recovery of our distillate. Okay. So what we want to do now is we want to factor out some terms here. So doing that, what we'll see is our vapor composition at infinity multiplied by our vapor flow minus our liquid flow over our partition coefficient. This is going to be equal to the composition of the recovery of our distillate, essentially. Okay, cool. So that looks good. From here, let's go ahead and divide this out. So we get this, the recovery of our distillate over what we factored out for here. Okay. So one thing we want to do from here is we want to essentially set this up as a summation, and this summation of our vapor composition at infinity is essentially going to be equal to 1. So going ahead and rewriting that, we get yi at infinity equal to 1. And this is essentially going to be equal to the summation at I for I equals 1. And it's going to be for the term that we just wrote just above. So just going ahead and rewriting that. Okay. And one thing we want to do from this point is we want to multiply our vapor on both sides. Okay. So we're going to be doing some kind of canceling out and such, but we're going to be multiplying our vapor from both sides. Okay. So solving for our vapor, what we get is the recovery of our distillate over 1 minus the liquid over our vapor times our partition coefficient. vapor flow times our partition coefficient multiplied by our partition coefficient again. Okay. So from this point forward, what we're going to do is let's go ahead and just combine some terms. Just make this, bring this out to our actual fraction. And what we get is the composition of the recovery of our distillates times the partition coefficients over the partition coefficient minus liquid over vapor. Okay, so this just kind of makes stuff cancel out and make it more sense. Okay, so what we want to do from here is we want to apply um, our heavy key, which is essentially J, and we're going to be dividing by KJ. Okay. Okay, so what we get here is we get this relative volatility coefficient that we worked on in the previous part. And it's going to be over our partition coefficient of the light key over the heavy key. And essentially this is our reference right here. Okay. Okay, so from this point we get our vapor, which is going to be equal to the recovery of our distillate times the relative volatility coefficient. It's going to be over the relative volatility uh, minus our liquid over vapor times the partition coefficient of our heavy key. And essentially this is going to be equal to phi. Yeah, it's going to be equal to phi. Okay. So now that we have this, um we can get our final expression for our rectifying. So it's going to be our vapor equal to the summation of I at I equals 1 or the recovery of our distillate times the relative volatility over the relative volatility again minus phi. Okay, so this is for our rectifying, and this is essentially how to find our vapor flow rate that we were kind of referencing up above. Okay, so I'm just gonna go ahead and I'm gonna write out what we what you would get if you were doing this for the stripping. So just to save some time, I'm gonna similar steps, but I'm gonna go ahead and write that part out. Okay, so now that we have this written out, essentially what's different from this is subtracting the recovery of our bottoms. We still have our relative volatility coefficients, but right here we're working with what we call omega. Okay, so now we have this rectifying stripping, we're going to be subtracting this from each other. Let me go ahead and write down some expressions, things to note. What omega is actually equal to, which is L bar over V bar times the partition coefficient of our heavy key. Okay. We also know that phi is equal to omega, and this is equal to essentially theta here. Theta, omega, and phi. I don't know how to write that. Okay. So now going and subtracting this from each other, we get V minus V bar equals our relative volatility multiplied by the composition of our distillate, the recovery of our distillate plus the recovery of our bottoms. Okay. And this is going to be over our relative volatility minus theta. Okay. Okay. So now that we have this subtracted from each other, there's some things to note. So this is going to essentially, our feed is going to be equal to our bottoms plus our distillate. So we can say that the composition of our feed is equal to the recovery of our bottoms plus the recovery of our distillate, which is essentially, oh, Okay. So which is essentially this is what we have here. Okay. So some things to know from this, we know that V is equal to V bar minus our feed multiplied by the one minus our quality. And if we rewrite this expression, we get V bar minus V is equal to our feed times one minus quality. Okay. So this is the vapor flow and our rectifying essentially this one. Okay. Okay, so now that we have this, we can rewrite this expression using this. So the feed times 1 minus quality is going to be equal to our summation of I at I equals 1 for our relative. So essentially just plugging in this expression right here for our terms that we kind of inputted for it. So this is going to be our relative volatility multiplied by the composition of our feed, and this is going to be divided by the relative volatility multiplied by, no, subtracted by what we have here, which is just data. Okay. So this entire feed is liquid. Um, so essentially our quality is going to be equal to 1. So we know that we can cross out these feeds, these cross out, and if our quality is equal to 1, this left-hand side will essentially be 0. Okay, so we can rewrite this and we get the same thing essentially multiplied by the composition minus theta. Okay, so this is essentially our final equation for Underwood to determine our minimum reflux. All right, so we're gonna go ahead and move on to our collab and code this. Okay, so we are starting the last part of homework 4. So, of course, we're gonna start by importing some things such as NumPy, our root scalar, and our make underscore subplots. As well as that, we also have the given that was from our problem statement. As you can see here, we have an equimolar mixture of 4 components with constant relative volatilities of 3, 2, 1, and 0.5. That is right here. Sorry. And that includes our 2 light keys and one of our heavy keys. Okay. And of course, that first equimolar mixture is what we have right here in this array. As well as that, we have our minimum. So we're essentially trying to determine our minimum reflux ratio. We're first gonna create a graph using of course, that root scalar that we're importing, and we'll see how that comes into play. We have a total molar feed molar flow rate of 100 moles per second of 0.99, 0.02, and 0 in the distillate product. And that includes these two right here, which is our feed total and the rectifying and the distillate. Okay. All right, so let's go ahead and start our code. Let me go ahead and run all of this. Okay, so we're first going to want to start by defining our Underwood equation. And for this, essentially, we're going to be using theta. Okay, so we're going to also want to return this value, but we're not just returning data here. We're returning what is the sum of first our alphas times our z's. And then this is going to be divided by our alphas minus our theta. Okay, go ahead and return that value. We're going to want to import our root scalar function. So for our root scalar function, this is going to be for our Underwood equation. And we're going to set up a bracket here. This bracket is going to be equal to this bracket is going to be equal to 1.01 and 1.99, right? Okay. Yeah, that's correct. 1.01 and 1.99. Okay. So let's go ahead and return that function. Something looks wrong. Under scalar, we have our underwood, we have our bracket, which is equal to, okay, so I believe I keep saying it's ambiguous, so I do believe that mistake comes from here. I closed off the parentheses here. Let's do it this way. Okay, let's go ahead and run all of this again. Okay, perfect. So we have our root function right here, and we're going to be coming back to that. Okay. So let's start by importing what we have known as theta plot, and this is going to be equal to our mp dot linspace of mp.linspace of 0.4, 3.1, and for 100 time steps. Okay. So we're also going to want to import a Underwood value equation essentially. So that's going to be Underwood underscore value equal to import a bracket right here. It's going to be imported to our Underwood theta for theta and theta plot. Okay. All right, perfect. Okay, so now what we can do is import, start creating our graph essentially. So fig equals make underscore subplots. Okay, so let's do a scatter. So fig that add underscore scatter from x equals theta plot, and y is going to be equal to our Underwood value. Okay, and then we can also update our layout. So fig dot update underscore layout, our width or our height, start our height is going to be equal to 400. Our width will also do 400, and we'll change our template. So our template is going to be equal to plotly underscore dark. Okay, let's go ahead and shift into that. Okay, perfect. Let's go ahead and increase some of these actually. Uh, Okay, I guess that looks better. So what we'll want to do now is solve for our reflux ratio essentially. So we're going to start by essentially looking at what the composition of our feeds is equal to in this case relative to what we are given in the problem statement. So ZF is going to be equal to our Z's up here times our feed total, so F total. Okay. All right, that looks good. So we're now going to want to import our vapor flow rate. So our vapor flow rate in this case is going to be equal to, go ahead and pause this. All right, so our vapor flow rate is going to be equal to mp.sum for the rectifying in our distillate, essentially. And this is going to be multiplied by what we just solved of up above, which is ZF composition of our feeds. This is going to be also multiplied by our alphas. And what we're going to want to do here is divide this by our alphas. And again, now we're looking back at our root function. So it'll be alphas minus what we had for this right here. So let's go ahead and take that and we're going to import it. Okay. Let's go and shift enter it. Okay, so now what we're going to do is essentially solve for our reflux ratio, and our reflux ratio is going to be equal to our vapor flow rate divided by mp.sum of our composition of our feeds times the rectifying of our distillates, and this is going to be -1. Okay. And now we can essentially go ahead and solve for our reflux ratio, and we get 1.16, which looks good. Okay, so let's go ahead and look back at our problem statement to sum this up. For an equal molar mixture of four components, we were giving all of these values in our problem statement. We determined what the minimum reflux ratio is using the Underwood equation for a total molar fluid, right? And essentially this graph is what kind of describes it from 0 to 3 with all these values.